Start with my collaborators, four of whom are here: Klaus, Juan Diego, Peter, and Denis. And there's a couple more youngsters we roped into this later on. The Red Stars were in on this from the beginning, so you can talk to them as well as me about questions about this work. So what we're going to talk about is the many-body quantum interferences that show up post the Ehrenfest time. And maybe I could just make a couple of comments. So it's these figures we actually want to understand before the end of the talk. First of all, there was a timeline in Alexander Altland's talk, and there was a beginning part, I guess up to time n or something. That's a little bit like the Ehrenfest time, and we're going beyond that, but not all the way out to the really long times out by the nearest, the mean spacing time scale, so not the Heisenberg time scale. Secondly, if I think about Ava's talk, the way I see the semi-classics she was doing, it's good if your system and the physics you're trying to discover get you to the to the Ehrenfest time, but it's not good post that. So you have to do something more if you want to include those kinds of systems. And then in terms of something Frank said, and when he was talking about IVR methods and so on, I would say I've almost never seen what I would call a complete semi-classical method applied to multidimensional systems. And by saying complete, I mean IVR methods, you're not actually doing all of the integrals. You're leaving some of them undone. And here, all of the integrals will be completely carried out. And so there's a difference in that sense. And one might have reasons for not doing that. And as I understand Frank's suggestion for why you wouldn't want to do what we'll talk about is because the boundary value problem is intractable. And so sometimes it's worthwhile beating your head against intractable problems anyways. So, you'll learn a little bit of something. Anyways, this is what I want to talk about. Okay, so not knowing what audience was going to be here and what everybody knows exactly, I'll just go through kind of some motivations for the context of what will end up being the discrete Bose-Hubbard model. And then we'll choose some initial states that are particularly well suited to studying post-Ehrenfest quantum interference in a many-body system. And then after going through that, I'll try to give you a flavor for how we worked out the semi-classical theory. So I will be doing wave packet propagation, and it's completely equivalent to coherent states if you map the parameters properly. So, what we're doing could be called complex WKB, generalized Gaussian wave packet dynamics, a saddle point approximation to the Feynman path integral or propagators. There's lots of different ways of referring to what we're carrying out, but I'll sort of, if you want to call it complex WKB or Maslow, that's one way to refer to it. And then I'll just talk a little bit about what we learned about how things go when you carry that out. So let's imagine, I'm a theorist, so this is my not very deep image of experiments, but I imagine you've got some counter-propagating lasers and you're creating 1 or 2 or 3 optical lattices. You make them deep enough and your atom's cold enough that they sit only in the lowest quantized site of each one of those wells. And there's an interaction between them, but they're in the same state. So basically the interaction is just counting the number of pairs inside of a site. And there won't be any interaction between sites in that sense, but there is hopping and through some tunneling mechanism or something to get from one well to another. And For convenience and for maybe some other reasons, we'll use periodic boundary conditions. There are ways to do that experimentally, but I'm not going to worry about that too much. So that's the physical system that one kind of has in mind. And there's motivations, physics motivations for thinking about this kind of system. It's a great way of studying far out of equilibrium dynamics for isolated many-body systems. And sort of my focus today, since this is a semi-classics conference, is more on the motivations about how does one go about developing semi-classical methods that you can actually carry out in multi-degree of freedom systems. And in this case, I imagine that as well isolated as these atoms are, as cold as they are, and as well isolated from the environment, if you had a macroscopic population, if you had millions of particles, you really wouldn't have quantum coherent effects at some level. So there is some macroscopic scale that's really mean field and classical. There's another scale where you have just a few particles that's what you would think of as purely quantum. But in between, there's a mesoscopic regime. Maybe you have 10 or 50 particles in a well, something where you're interested in the quantum interference, and it's isolated well enough to think about quantum interference, but it's also starts to get difficult to think about from some just purely quantum method. And besides, semi-classics gives you understanding that you don't get by just being able to do quantum calculations. We're going to put quantum interference into the mean field equations, if you like. And the Ehrenfest timescale, we're interested in what happens after the initial that initial dynamical period. So we have to sort of answer the question of how you actually implement complete semi-classical theory in a many-body multidimensional system. And really, it is the boundary value problem that you have to spend the most time on. So, you know, where are the saddle points? In this case, they're complex trajectories, so we're going to have to deal with complexifying everything. And of course, that makes the boundary value problem more difficult at some level, but it doesn't really. You just think it does until you work on it. And then there are some goofy things which I won't talk about, but it's the geometric phase index is not as trivial as you might think, but I'm not going to talk about it. You just have to get it right. So in terms of questions, you might ask, will this actually work? How does it depend on the number of particles? How quickly does it get better? Or what kind of dynamical regimes can you get it to work in? And how long in time can you get the details of the quantum mechanics correct with this kind of an approach? And then there's all kinds of things that break down semi-classics that are well known, but it gets kind of hard to figure out when you see something not working and you're in a high dimensional phase space. It's not that trivial to know exactly what's giving you problems, but some of these sorts of things are what we run into. Okay, so this leads me to the Bose-Hubbard Hamiltonian. And for today, I'll just show some results for 1D rings. I'll show results, well, you saw on the first slide, a 4-site ring and a 6-site ring. So L is the parameter for the number of sites in the ring. I've done some 2D calculations as well, but I'm not going to show anything about that. The parameter for the hopping or tunneling strength is J. U is the on-site particle-particle interaction strength. The energy and particle numbers in this Hamiltonian are conserved, so you have two conserved quantities, constants of the motion. And there's these two parameters, the filling factor, the total number of particles divided by the numbers of sites, and the interaction strength divided by the hopping strength ratio. And it's really the product of those two parameters that are the most important for what we're doing. Symmetries enter into this a little bit. I'm not going to go into this very much. But you do see the U1 symmetry in the classical mechanics as a rotation symmetry of your phase space trajectories. But we'll come back and see some effects on the saddles due to the permutation symmetries of the ring geometry. Okay, so if I were an experimentalist, I'd probably be interested in the expectation value of some operator, but in a sense, to understand the post-Ehrenfest quantum interference, it's a lot better to look at a matrix element of the propagator itself. So that's going to really display a lot of interference phenomena, and that's actually going to be quite a challenge for the semi-classics to get right, because all of the interference has to just be done perfectly, or you'll get nonsense. So that's actually, for a theorist, that's an ideal quantity to look at for this. And in this case, we'll talk about coherent states, and through its equivalence to wave packet dynamics, it's completely equivalent whether you're talking about the quantum dynamics of coherent states or wave packets propagating. So there's no real reason to make any distinction there. And then I'll actually Fourier transform the results to show you how much of the spectral information is contained in the actual semi-classics we're able to calculate. We can't get to the Heisenberg time, but you can still get an enormous amount of spectral information from the early time interference as well. So we'll see that in a second. Okay, so our coherent state, whatever number of sites we have, we pick a z value for each one of those sites. We have this this construction that's properly normalized, and a nice far out of equilibrium initial state is to take a density wave in which you have a coherent state with a population in, let's say, every other site, and the ground state or the empty sites on the other set. And in this case, then that makes your filling factor the mean occupancy of those levels, of those sites, divided by 2. There's 2 important time scales. I'm actually going to show results that are closer to the strong interaction regime than the strong hopping regime. And so these 2 time scales will show up in the actual quantum results pretty clearly. So let's get back to this first figure. The blue curves underneath are quantum calculations, and they're just reflected so that you can distinguish them from the semi-classical calculations. So the red curve is a semi-classical. The upper figure is a 4-site ring. The lower figure is a 6-site ring. And you can see pretty clearly that the onset of interference phenomena is right about here, so the Ehrenfest time is from here onward. If you don't fully implement your semi-classics, you're basically done here. So in this case, we've got a mean of 20 particles in the first and third sites, and in this one, it's in the first, third, and fifth, 10 particles. And when you calculate the amplitude, a survival amplitude, you get a curve like this. Now, this object here is the revival time. There's hopping, but you haven't completely destroyed the revival that's in the system. And this is the 1/3 and 2/3 revival. This is where the half revival time is. And you see that structure still, but there is significant hopping. It's just all of that structure has not yet disappeared. So the hopping is not so strong that that's gone away. Okay, so if you look at the details, you can see that the semi-classical theory or calculations is following the quantum calculations extraordinarily well. And there's a third curve on these figures, which is a truncated Wigner approximation. And this is essentially the theory without the quantum interference built in. So you see that it just quickly comes to a constant, essentially constant value, and from then on just stays there. So if you don't put the interference in, that's all you can get out of this. Okay. if you do have the interference and you Fourier transform it, this is how much of the spectral information is contained in this. So obviously, if this were perfect, it wouldn't go below 0, but it's a finite time, and and so there's some oscillations. But if you look at a blow-up of this region up here, you can see that that once you start getting all the right interference phenomena in there, you get a lot of the information about the spectrum built into it. So no, we can't get all the way to the Ehrenfest, to the Heisenberg time, but you still can get a lot of physical information out once you start to incorporate interference correctly. So how do we do it? Well, first, you start with the mean field relations, and the way I decided to do this is first use the commutation relations to put the Hamiltonian in a left-right symmetrized form. Start there, then make the substitutions where the annihilation and creation operators are replaced by the quadrature operators, position and conjugate momentum. That gives you a classical Hamiltonian. And then the last step was to identify exactly what the coherent states corresponded to in terms of their wave packet equivalence. So if you start with this this parameterization of a wave packet, and one of the reasons for putting it in this form is by putting the h-bar here, the position of the saddles become completely h-bar independent, so you can study things. You can have problems in which you vary h-bar and your saddles will be invariant. So that's one thing. And the factor 2 is there, so I don't have to put it in a bunch of other places. The Wigner transform of this state is given here, and these shape parameters B, this doesn't have to be real, and when you put a complex piece in it, you put a momentum position correlation into the state. You put a phase oscillation into it. But anyways, you can account for that if you want to, and that gives you momentum position correlation blocks in your shape matrix of your Wigner transform. That is determinant 1. You can prove that that form is, and if you do this, then that's the exact Wigner transform for that. So, yeah. I mean, in a sense, h-bar is 1 here, but yes, you can do things like that. There is a transformation to this problem so that you could actually just change particle number and the saddles would be invariant, and you could just do a pure study of how everything is changing with particle number. There's a way to do that. But that's part of it. I mean, the saddles wouldn't move if you keep this straight. Okay, and it's not worth going into, but the Z is just the translation parameters, and the ground state Hamiltonian is what determines all the shape parameters. Just for curiosity's sake, I had to work it out for myself. If you want to have a chirped ground state, you have to have this kind of px term in your harmonic oscillator to rotate your Wigner transform to any angle or whatever. That does it. So anyways, we know the mapping, and we're good to go. So if you really look at what people have called a semiclassical theory to some extent, it's the truncated Wigner approximation. But I'm going to call that classical and say that because it's not really including quantum interference, that's not what I mean by semiclassical. So in this case, you would take the Wigner transform, take the Poisson bracket with the classical or the mean field Hamiltonian, and that propagation using that density would then give you a way of calculating truncated Wigner approximation calculations. So that would use that part, but we're putting quantum interference into this now. So what do I need to do? Let's just take the coherent state beta equal to alpha, so we're looking at a survival amplitude. Just for simplicity, you propagate your wave packet, you overlap it with itself. What you have to do if you want to fully identify, your saddles, is you find the Lagrangian manifold underlying your coherent state or wave packet, propagate it classically, intersect it with the appropriate Lagrangian manifold for the final state. And then you have to calculate the quantities that you're used to with semiclassics and put it in the saddle point expressions. And in this case, you're forced to go to a complexification of the classical mechanics. So in your classical Hamiltonian, this P and Q is now complex. So that's what we're going to do. And so there's sort of some problems in implementing this. These equations right here, you can find in the Huber-Heller-Littlejohn paper, except I think maybe the H-bar is still in it, but I've scaled it out the way I put and there's a 2, I think. But otherwise, those are the equations that's in the 88 paper. That's the boundary value problem that you have to solve with complex position and momenta. And the thing that I find amusing is, at any time, there's an infinity of solutions. As long as you have a nonlinear system, you have an infinity of solutions, and you have to throw away an infinity of those choices. You really only have to keep a couple. So if you're going to solve the boundary value problem, it's good to start with a method that doesn't find the infinity to begin with that you're going to throw away. I mean, that's kind of helpful. There's what I would call microscopic search domains. I mean, if you think of a saddle as just a point in a space, that is microscopic, but I'm going to rely on a kind of Newton-Raphson method, and there's a domain of convergence around that saddle, and those things are incredibly tiny. So you have to, when I say microscopic, you have to somehow find the environment near a saddle so that you can actually locate the saddle itself. So these things are microscopic in high-dimensional spaces, and the more chaotic the system is, the more microscopic they are. That also happens. You have these runaway solutions where the momentum goes to infinity in finite amounts of time. You have the problem with semiclassical divergences. And then just as another technical problem, for every saddle you find, there's actually an infinity of saddles, because if you fix a saddle at one time and then you differentially change the time on a slightly different energy surface, you'll have a related saddle. I mean, one that continuously deforms from that one. So you have to actually, for a continuous, if you're not studying maps, if you're studying continuous time dynamical systems, then you have to get the whole family of saddles for each saddle you find. So when I count saddles, if I say there's 800 saddles, there's 800 families. So there's just work involved. You just have to do it. But it's a technical problem. So let me just show you what I mean. This is one saddle. And this is one that's really nice in the sense that if you go truly into the H-bar going to zero limit, so as you change time, you're changing energy surfaces, and when you change energy surfaces, you necessarily change dynamics unless you have a homogeneous dynamical system. So you could go through orbit bifurcations, you could cross Stokes lines, you could have things that go wrong. But in the H-bar going to zero limit, your energy surface over which this thing's contributing would be so narrow, the dynamics wouldn't change enough. And then you would get this characteristic shape for every saddle family. That isn't what we find. We get some like this, and then we have some that are more problematic. But when you see those problems, you know something's going on. So it gives you information. When you see this, you're happy. When you don't see that, then you know something's going on. So I have examples where it tails off here, and then before it gets smaller than my cutoff, it goes off to infinity and blows up, and I have an infinity in the thing. Or I have others or I have double humps, and you know there's some kind of orbit bifurcation nearby or something. So all kinds of things happen, but this is what happens in the good case. And the peak contribution occurs when the number of particles and the energy are close to the expectation value of the coherent states themselves. So the expectation value of energy or the number of particles, when that's near the peak of that saddle family. So in this case, short time is the high energy and long time is the low energy surfaces. And likewise, short time is the high particle number, long time is the low particle number. All right, so how do you find these complex saddles? Actually, the first thing is, if you just think physically, every classical transport pathway that you can see by your eye, if you've ever watched waves, has to have a saddle associated with it. And you can put those classical transport pathways into a one-to-one correspondence. So what you can do is first imagine real trajectories that get you from some place to another, and then in the neighborhood of that, there has to be an actual complex saddle. And you'll find that if you use a Newton-Raphson technique, there's a one-to-one correspondence. Now, when you start using complex trajectories, the thing about tunneling gets a little bit vague. You know, it's not exactly clear what's classically allowed and what isn't necessarily. And so in this case, there are ways of, let's say, varying parameters and watching something disappear classically, but not necessarily the saddle. I'm not going to do that. I'm going to forget about all that. I'm just going to keep the saddles for which I've put into a one-to-one correspondence with the classical transport pathways. So that's what I'm going to include. Okay? So in that sense, I'm forgetting tunneling, but I'm not saying you can't actually incorporate that. So let's see, 17 minutes. So how do we do this? Well, we go back to our Wigner transform, and if you think about dynamics, this is a hyperellipse in some orientation, rotated however it is, and once you start propagating it, it's going to distort and stretch. Now, so long as it looks like that, you're not yet at the Ehrenfest time. Once you get to the Ehrenfest time, that thing's folded over and it now has multiple sheets. And it's not just a straight object, it's curled all over the place and has some crazy deformed shape. Okay, that's fine, but each of those sheets is then going to get associated with a unique saddle trajectory. So we're going to have to keep track of that. But first, we have to know where to search, and this is the key. This hyperellipse has what you might call, I don't know, the equation for the ellipse. Think about differentially around the center of this wave packet. How do I want to explain this? Maybe I should start the other way. Every dynamical system has structural features. Like if it's chaotic, there are stable and unstable manifolds of the shortest periodic orbit. There's tori in it. There's an energy surface. There's a stable direction this way. There's an unstable direction that way. Those features are like the infinite time features of the dynamics. What you need to find is in the neighborhood of this wave packet and its distribution and density, how do those invariant structures or infinite time structures slice through that zone? That's what you're trying to find. And in a high-dimensional system, that's not so obvious. If you just have a 2 degree of freedom system, you can draw it and look at it and figure it out. But if you have a lot of degrees of freedom, then the idea is you can still figure that out by looking at the central trajectory, propagating it long enough in time, all of the distortion of that ellipse will rotate along the asymptotic directions, and if you've gone sufficiently in time, they've converged close enough to that asymptotic structure. So what you need to know is that asymptotic structure. In this case, the shape parameters transform this way on the ellipse. Now I use the inverse of that, but it doesn't matter. That object is the thing that has It's a real symmetric matrix with a spectrum and orthonormal eigenvectors. And once you know what directions are what and how the eigenvectors are associated to them, you can pick off the most unstable directions, or you can actually reduce your search to only the physically relevant part. And that's the idea. And then there's one slight complication, which is that the orientation of those vectors is what they are at the end of your trajectory. So then you have to take some vector of interest, back transform it to where you started, and that's the actual search direction. So, you know, you just have to figure this stuff out and do it. Then you use your Newton-Raphson technique, and you're ready to go. So, so let's take a look at the Forsyte ring. So in theory, if you don't think about what you're doing, to find the boundary value solutions, you have to do an 8-parameter search. But in reality, you only have to do a 1-parameter search. So you can get all of the saddles by doing a 1-parameter search in this case instead of 8 parameters, just because you sat down and thought about what you were doing. So that is a good reason to do that. Now, if you look up here on this figure, this is a plot of where trajectories left the neighborhood of the initial phase space blob and got close back to where they were. Every one of those dots is showing you kind of the search domain, or sort of the Newton-Raphson kind of. They're bigger than the actual convergence domain around each saddle. But that's sort of the idea, but that's just one dimension. If you were actually looking in the full space, you'd be in a 16-dimensional space, and those dots would be really actually quite microscopic. But since you only have to search in this one dimension, you're actually able to find those things. Plus, there's a symmetry which shows you that all of the saddles below that axis are identical to above that axis, and so you only have to find the ones above the axis and on the axis. So there's lots of little things like that you can do to make your life simpler. But for the 4-ring site example that I showed you, as a function of time, this is the number of saddles, and each one of those requires the construction of a whole saddle family. But you see, by the time you got out to t equals 14 or 16, there were 800 saddles necessary to get the semiclassical theory correct and to get all the constructive interference correct. So if I go back to this figure, when you look at these oscillations in this range right here, there's 200 or something like that different chirps, or I don't know if you want to call them chirps, but 200 of things that look like this that you've added up to give that set of oscillations. If you have even small phase errors, you'll just get random noise. So the fact that they correspond means you really nailed it. So that's encouraging. For the 6-site ring, you would have to do a 12-parameter search, but you can actually find all the saddles for this problem with just a 2-parameter search. And then they have this cute hexagonal structure due to the symmetries of a 6-site ring. The saddles in this section are reflected to give exactly the same saddle in the I- section, and then the 2 and 2+, those are identical. So all you got to do is take this section and this section, and you've got all the saddles. And then from there, you can get everything. It's kind of interesting that the symmetries take time to fully be exposed by the saddles. So as you go out in time, at first you have high symmetry saddles, then slightly lower symmetry saddles, and eventually no symmetry saddles that come in multiplets. And so there's a time scale for how discrete symmetries behave in the quantum dynamics that's kind of interesting. And this whole method gives you ways of very quickly searching through the dynamics of a model like this certain parts of the phase space are regular no matter what interaction you take. This happens to be the part of the phase space that's the most unstable of all in all of the Bose-Hubbard parameter possibilities. And this one shows a case that goes through an incredibly abrupt and universal transition in the dynamics. And we figured out that that's related to the later, not right away, but to the self-trapping transition. You can modify all of this stuff to find periodic orbits. It's really trivial. So you can find periodic orbits, and basically all of them if you want, in these high-dimensional spaces as well. So you could actually, if you were interested in that, do that sort of thing. So let me sort of end there. This stuff works pretty well in some domains and can actually be carried out. I mean, it's not like I'm claiming to have solved the boundary value problem, but there's whole classes of dynamical systems where this will work, where many of the degrees of freedom aren't needed to be searched, and so on. We were able to do multi-dimensional systems, so that seems, we were pretty happy with that. So I'll stop there.